A loudspeaker emits sound towards the open end of the pipe, the other end is closed, the standing wave is formed in the pipe. Okay. The diagram represents the displacement of the molecules of air in the pipe at an instant of time. Right. So there's a wave which comes over here, sound wave, a longitudinal wave which comes over here, and then it gets inside the pipe and it forms a stationary wave. Okay. The wave will now come like this. Okay. And now outline how the standing wave is formed. Simple. You need to explain what is the standing wave, how is it being formed. How many marks? 1 mark. Okay, so what you should do is that the incident wave from the loudspeaker enters the tube and gets reflected from the walls. The superposition of incident and reflected waves gives rise to the standing wave. Okay, so this is what you need to mention. Next. X and Y represent the equilibrium positions of two air molecules in the pipe. Two equilibrium molecules in the pipe. Okay. And then, see, when you talk about an equilibrium molecule, it doesn't mean that they are to be stationary. Okay. Equilibrium means there are two forces that are acting at it, and both the forces are equal to 0. And the arrow represents the velocity of the molecule at Y. Arrow represents the velocity of the molecule at Y. Okay. And then draw an arrow on the diagram to represent the equation of motion, the direction of motion of the molecule at X. So what is happening to the particle at X? You know, so they are vibrating like this. The vertical forces are definitely 0. Okay, but they are still vibrating like this over here. At this instant, vertical force is 0. Okay, but after some time, what happens is it has a vibration like this. Now what happens is X. Now what is happening is that, see, the particles which are present here is a longitudinal wave, right? These particles will now start vibrating like this. Okay, and then they pass on the energy from one end to the other end. I think I made a mistake in mentioning vibration happens like this. Vibration doesn't happen over here. Okay, this is a representation of this one here. Okay, so therefore the particles will now start vibrating like this over here. So as a result of it, this particle will also tend to go like so. You need to mention the arrow in this direction. Next, draw an arrow in the diagram to represent the direction of motion of the molecule at X. Label a position N that is a node on the standing wave. Where is the standing wave's node present? There is a node which is being present on this standing wave at this point. You can mention this point. Okay, and then next, the speed of the wave is seen to be 340 meters per second, and the length of the pipe is 0.3 kilometer. Calculate in hertz the frequency of the wave. Now, if you look at this here, if this is node, this is also a node, this should be an antinode. So the distance between two nodes is given by lambda divided by 2. And distance between these two is given by lambda divided by 4. The total distance starting from here to here will be 3 lambda by 4, which should be equal to the length of the pipe. Okay. Now 3 lambda by 4, 3 lambda by 4 is equal to the length of the pipe, which is equal to 0.3 meters. So lambda will thus be equal to 4 into 0.3 divided by 3, which should be 3 ones are here, it should be 0.4 meters. Now what is he asking? He is asking you to find out frequency. Frequency is equal to V by lambda. V equal to F lambda, right? So what is V? 340 divided by lambda. What is lambda? 0.4. When I do this one, so what is the answer I get? That is your final answer. So it should be 340 divided by 0.4, it will be 850. 850. How is the mark distributed? This is for 2 marks over here. So 1 mark would be in the calculation of the lambda, 1 mark in the calculation of the frequency. Okay, next. The loudspeaker in A now emits sound waves towards an air-water boundary. Air-water boundary. Okay. So here it is air, here it is water. Okay. ABC are three parallel wavefronts emitted by the loudspeaker. The parts of wavefronts A and B are in water are not shown. Okay, only in the air the wavefronts are shown. Nothing else is shown. Okay. Wavefront C has not entered the water. Okay. The speed of the sound in air is 340 meter per second, and in water it is 1500 meter per second. So I will write here directly. This is 340 meter per second, and this is 1500 meter per second. Now by looking at it, can you tell me which is the rarer, which is the denser here? The rarer medium is one where the speed of light or maybe sound is higher. Okay, so therefore this would become a rarer medium, this would become a denser medium. Now what's happening? The ray is going from a denser medium to a rarer medium. Okay, so whenever a ray goes from a denser to a rarer, and if it exceeds a critical angle, then what can happen? PIR can happen. Okay, but we do not know what's happening over here, but we just understood this one. See, when you read a question, as much as possible try to extract information and then proceed further. Okay, do not just say we'll wait until the end of the problem and then get the parameters. That's wrong. Okay, and then wavefronts make an angle theta with the surface of the water. Determine the maximum angle theta max at which the sound can enter water. Maximum angle. Okay, so initially, see, this is your wavefront angle. Now if I want to get the ray angle, because you have learnt all this in rays only, so what I will do is I'll first draw a line like this. What is this? This is your normal. Your O is your normal over here. If this angle is theta, this angle should also be theta. Right? If that angle is theta, this is 90. This should be 90 minus theta. This should be 90 minus theta. Right? If if you want to take this, okay, let us look at this one here. See, this O, let me call this point A, or maybe let me call this point Q, because ABC we already used. O, Q, and let us have R. Let me write it down in a bigger way here. This is your point O. This is your line, which is your wavefront as shown. And this is your wavefront, extended wavefront B here. And this is your point Q. And this edge, okay, here, this is your R here. There is the R here. Right here. This is your R. Okay, so if this angle is 90 minus theta, this angle is 90, then this angle should be theta. What is this now? This is your incident ray, this is your normal. So angle of incidence is theta. Okay, I just wanted to show that this angle is theta. Okay, so therefore your angle I is equal to theta also. Okay, now he is asking you what is this maximum angle. See, rays can easily enter in this case, but if you keep on moving this circularly, let us say if I keep the loudspeaker here, there is a possibility that the rays can come here and get reflected like this. Why? Because it's going from denser to rarer, and therefore there is a possibility of the total internal reflection possible. That means there is one particular maximum angle. What do you call that angle? Critical angle. He is asking you to find out what is a critical angle. Nothing else. Right? To get the critical angle, what is that you use? You generally use this as, if I say this is my refractive index N1, this is my refractive index N2, I will write N1 sin theta or sin theta max, or maybe I'll write N1 sin C is equal to 1. The sin C was nothing but your max in optics, right? N1 sin theta max is equal to 1. When do you consider this 1? When this is your air, but here it is water only. So therefore, I should write this as N2 here. I write this N2. Okay. Now we have arrived at the equation. So for 2 marks, so many things are communicated. Okay. So now you have N1 sin theta max is equal to N2. What is the value of N1 and N2 known? It's not known. First of all, we are talking about sound. You are bringing in the refractive index. These are 2 different things, right? How can I put it? I can definitely put it. Okay. Now what we'll do is, concept is same. So N1, what is N1? Refractive index. How do you define refractive index? This is your rarer medium. I will say refractive index of the velocity of the sound in rarer medium divided by C by V1 into sine theta max is equal to C by V2 so this is what C by V2 over here. Now if you look at this over here, C by V1, what is C? C is nothing but the speed of sound in air, which is 340. And what is this V1 here? This is the speed of sound in the medium. Which is the medium over here? Sorry, this is your 1500. This is your rarer medium, right? This is your rarer medium, 1500. And what is V1? V1 is a denser medium sound, 340 into sine theta max is equal to, what is C once again? Rarer medium. Rarer medium is 1500 divided by the next medium. What is that medium? This is 1500 once again, right? These two will cancel. So because if V1 is 340, V2 should be 1500 only. Okay. So now what we have here is that we will have sine theta max is equal to 340 divided by 1500. Let us calculate this value. Should be 340 divided by 1500. I get 0.226 2266. 0.2267. We have a recurring decimal, so I will put this 67, and I want to get the value of theta max over here. Go here, you can use your this was over here. Trigonometry second. Just let me figure it out. Or if you find it out, I do not know how to get this one here. And if you find out that 340 by 1500, and then you will get theta max to be equal to 13. Okay, find out using your GDC. So I think draw lines and diagrams to complete the wavelengths A and B for values of water less than theta max. Okay, if it is less than critical angle, where will this go? That's the question. So if it is less than theta, this one over here. So this could be, let us say for example, this is your, let us say I get something like this over here. So this is your critical angle and this is your incident ray. Now this is your denser to rarer. So this will go like this one. Go like so, right? So therefore, how do you write the rays over here? You have to write the rays like this. You have to write the rays wavefront like this over here. But you should not write here in this direction. You should continue with this, this one. So what you do is, whatever line I have drawn here, draw it parallelly like this. Okay, draw it parallelly like this. But why do you write this? See, what can happen here is that, see, this distance is small, this distance should be large. So you're seeing this one here. So therefore, it's the correct way to write. Okay. So with this, we come to an end to this problem. See you next problem.